Hello everyone, welcome to the third portion of 18th lecture on scalable data science. I am Professor Shourangshu Bhattacharya from Computer Science and Engineering Department at IIT Kharagpur, and the topic of today's discussion is Hadoop systems. So, in the previous lectures we have discussed what is big data and Hadoop, what is MapReduce. We have seen some example MapReduce programs. We have seen HDFS commands and internals, and we have seen some implementation of MapReduce programs in Java and other languages through streaming API. So, in this lecture we will go into the implementation details of the MapReduce framework, and specifically we will look at the implementation of sort and shuffle. As we discussed, this is an important component and this is the main component which is important for scalability of any MapReduce program. We will see how the master or the app master coordinates with the mapper and the reducer tasks. Then we will see how fault tolerance is implemented, which is that if a particular mapper or a reducer tasks fails to respond, how does the app master recover from this situation. Then we will see we will see the notion of pipelining of map and reduce tasks, and finally we will see some refinements which help speed up a MapReduce program. So, we have seen this overall picture where basically a MapReduce program consists of multiple jobs, and each job has a app master which coordinates between various map or reduce tasks which are needed to be executed in order to complete this job. Now, as you have seen, one of the as you have seen, the parallel picture for a MapReduce tasks is that several mapper tasks get executed in parallel, possibly in different machines. Now, these mapper tasks produce some intermediate results. Intermediate records, let us say. Okay. These mapper tasks produce some intermediate records. So, for example, in case of your word count program, these intermediate records were of this form word and then comma 1, okay. And there were as many records of this form as there are words in the whole file, and now we are having a big data. So, possibly the number of intermediate records is going to be very high. So, now what do we do with this? What does the MapReduce system have to do with these intermediate records? So, they have to ensure that the intermediate records with the same key, in this case the same word. So, word is the key here. Okay. So, the intermediate records with the same key reach the same reducer, and this operation is called the shuffle or sometimes sort and shuffle operation. Okay. So, the question is, how can this operation be executed in a scalable manner? And the key to this lies in distributing the tasks in different portions. So, for example, if the first thing that that is done on the mapper side is what is called the sort operation. So, sort operation sorts each record into different buckets, as you can see the buckets here. So, it in some sense creates the outputs for each of the reducers. Okay. So, how does we will come to how the sort operation computes which records will be put in the same bucket. Okay. So, in order to map records to buckets, the mapper function may use something like a hash function or some other partition function. Okay. So, this basically partitions the mapper output records into different buckets based on the mapper output key. So, this is the first step. Okay. The second step is that it should know where the output of each bucket must go. Okay. So, both the mapper and the reducer must know. So, the reducer should know. So, for example, the first bucket should go to the reducer 1 and the second bucket should go to the reducer 2, and this should happen for each mapper. Now, both the mapper and the reducer should use a consistent hash function, the same hash function, in order for this to happen, because the reducer knows the records or the keys that will come to it, and hence it can provide the hash to the mapper. Now, this phase is called the copy phase. So, first inside the mapper there is the sort phase, then there is a copy phase where the reducer asks for records in a particular bucket from each of the mappers. So, this phase is called the copy phase, and then finally in the reducer there is a phase called the merge phase. So, the merge phase basically merges the records which have come to a particular reducer into one single sorted list. Now, here note that since individual lists retrieved from all the 3 mappers are sorted, this merge function can be easily executed. So, this is an order n function. Similarly, the sort function is an order n function, because all the mapper has to do is it has to compute the hash value for the partitioner value for the mapper key, and then put the record into different buckets. Okay. And the copy phase is a network heavy phase. So, the copy phase is a network, is in fact it is the only network operation that is done or the large scale network operation that is done while executing a MapReduce framework, a MapReduce job. Okay. So, and this so we will see how to speed up this copy phase more. Now, note that, so this is a zoomed in view on what happens in each mapper site. So, as the mapper function is executing, it is producing more and more mapper output records. Okay. So, the mapper output records is are being partitioned and sorted, and it is clear that this mapper output record cannot I mean it may so happen that all the mapper outputs record from a given mapper will not fit into the mapper memory. So, these have to be written to the disk. Now, in which disk is this written? Okay. So, so we will come to that, but so once this is and this happens in many phases, and then there is a local march on disk inside the mapper task which is executed before the copy phase is executed. Okay. So, basically the mapper outputs record are written to the local file system by the mapper. Now, when the copy phase starts, the reducer calls a fetch on the mapper task to give it the appropriate partition of the data. Okay. So, and now it receives many such partitions which are sorted in themselves. So, as they receive these sorted data, they merge and store it, or the reducer merges and stores it into its local file system, because again the reducer input record need not be there, or it may be that it spills from the memory. So, this merge also actually is executed on disk. However, the key thing here is that both on the mapper side and on the reducer side, it is a one pass operation. So, one pass through the data is able to achieve this whole either the partitioning of the data on the mapper side or the merging of the data on the reducer side. This is very important for fast execution of the MapReduce task. So, as we have discussed, the input and output and the final output are final output of the reducer task are stored on the distributed file system. So, these are fault tolerant by design. However, the intermediate results are stored on the local file system of the map and reduce workers. Okay. And the output of one MapReduce task is often an input to the other MapReduce task. Okay. Now, how does the master, so as we have discussed, the master node takes care of the coordination between the different mapper and the reducer's task. Okay. So, basically what happens is for every task that the master node spawns, the task is either in idle state or in progress or completed state. Okay. So, initially all tasks are idle, and as more and more workers become available and the tasks are ready to be executed, their status gets the idle task gets scheduled and they become in progress tasks. So, the other thing is, when a map task completes, it intimates the master that it has completed, and it sends the master the location and the sizes of its intermediate files, and then the master gives this info to the reducer, which then calls talks to the mapper tasks for a fetch from the intermediate result. And of course, the master pings the workers periodically to detect if there are any failures. Now comes the important issue of fault tolerance, because as we have seen in the big data world, the fault tolerance is a very important requirement. So, there are roughly two components where fault tolerance is important. The first is HDFS, and we have seen how it achieves fault tolerance through replication. So, we can assume that whatever data is stored on the HDFS is tolerant to failure. Now, on the MapReduce front, while a job is being executed, one still needs fault tolerance. Okay. So, the fault tolerance is achieved by restarting. So, the master restarts the map and reduce tasks which have failed, and it can write map output to the file system, to the distributed file system, to minimize recomputation at certain times. However, so we go into detail of task failure. So, detail of failure. So, the first, so as you have seen, there are three main components of any MapReduce task. One is the tasks, either the mapper tasks or the reducer tasks, which get executed on the nodes. So, the second important component is the application master, which coordinates and controls between the task, and finally, there is the node manager, which basically coordinates between the different nodes of the cluster. So, all these three can fail. So, if the task fails, it is known to the node manager and the app master, and so the app master periodically pings the tasks, and if they do not get the response from the task, then they assume that the task has failed. Similarly, application master sends heartbeat to the resource manager or the node manager. So, if the resource manager fails, then the application master knows that, or if the application master fails, the resource manager knows that the application master has failed, and then it restarts the entire job. Okay. Whereas, if only tasks fail, only those tasks need to be restarted by the node manager. So, now we see that how task failures are dealt with. So, the first is what happens if a map worker fails. Okay. So, map tasks completed or in progress at worker are reset to idle. So, first the app master resets a failed map task to idle, and then the reduce workers are notified, and when the task is rescheduled, the reduce worker gets the input from this rescheduled tasks. If a reduce worker fails, then only in progress tasks are reset to idle. Okay. Completed tasks need not be reset to idle. So, completed tasks are remain completed. Okay. And then the reduce start is simply restarted. In the first case, even the completed mapper tasks need to be restarted, because the input of that mapper task needs to be read by the reducer. In case the master fails, as we have discussed, the resource manager will abort the job and a new job will be started. So, that completes our discussion on how various aspects of the MapReduce framework is implemented. Now, we discuss some issues which need to be resolved for every MapReduce program. So, the first issue is how many mapper and reducer jobs should we use. Now, let us say there are m mapper jobs and r reducer jobs. So, typically in order to take care of or take advantage of the maximum amount of parallelism, the number of mapper tasks can be 1 per DFS chunk. So, in this case also called, sometimes called splits or just blocks. So, in the DFS terminology this will be called blocks, and in the MapReduce terminology this will be called splits. So, the number of map tasks typically can be the same as the number of splits of data or number of blocks of data that are input to the mapper. If there is a large number of mapper tasks, this actually improves the overall performance, it improves the load balancing, because then each mapper tasks is not working on a huge amount of data, and that helps the scheduling of different tasks, and also it speeds up the recovery from the worker failure. In fact, it is, if the mapper task is very small, it is unlikely that the failure will occur to a mapper task. Now, the other thing is the number of reducer tasks. So, the number of reducer tasks typically depends on the job. So, for example, in the word count program, the number of reducer tasks is upper bounded by the total number of words which are present. So, in general or typically the number of reducer tasks needs to be provided to a MapReduce job, otherwise it can be taken to be default value, something like which is set by the cluster. So, something like 10 or 15 as depending on the number of nodes in the cluster. Now, we discuss the idea of pipelining. Okay. So, as we know that typically we will have a large number of mapper tasks. Okay. So, what the app master does is it pipelines the mapper task. So, for example, you can see that there are 3 mapper tasks in this case. 2 mapper tasks are scheduled on worker 1. So, the first mapper task ended in a very short time, and the second mapper task was scheduled on worker 2. So, the third mapper task was again scheduled on worker 1. So, it is very common to have a pipelined execution, that is one after the other execution of mapper task on the same workers. Okay. And then one can do pipeline shuffling for map execution for better dynamic load balancing. And then one can so once the reducer tasks can be scheduled on other machines which read from different mapper tasks, as is seen here. So, read 1.1 is basically the read of mapper 1's output, which starts when the mapper 1 ends. Then read 1.3 is the read from mapper 3's output to reducer 1's output, which starts when the mapper 3 ends, and then finally when the mapper 2 ends, then we can execute read 2.2. Now, many a times what happens is that out of a large number of mapper tasks or even reducer tasks sometimes, a few of the tasks are very slow. So, these are not failures, but these mapper tasks are execute in a very slow manner. Okay. So, so there comes a stage when most of the mapper tasks are over, and this could be because of many reasons, like that particular machine is having a hardware problem or bad disk or some operating system problem or something like that. Okay. So, in this case, sometimes the overall job execution time becomes unnecessarily high, and the workers and the, for example, the reduced workers are also waiting for these slow mappers to end. Okay. So, while maybe other machines are free to run the map job in a fast manner. So, in this case, the solution becomes that near the end of the mapper tasks, what the master does is it schedules backup tasks for the in progress or for the in progress map tasks or reduced tasks. So, and whichever, so now for the same map task or the reduced task, there are actually getting executed on two machines simultaneously. So, this shortens the total job completion time, and then the protocol is that whichever of these competing backup tasks ends first, the output of that backup task is taken, and then the other backup tasks for the same task are ignored. Okay. So, this is another improvement. Okay. Another improvement is that is one of combiners. So, as we have seen, the mapper produces many outputs of the form key comma value. Now, it may so happen that for the same key, a single mapper produces many records. So, then in theory it is possible to combine all these records into one record, and thus saving and thus reducing the number of intermediate records by a lot. Okay. So, this is the task of the combiners. Okay. So, combiners can be thought of as something like mapper side reducer or reducers which work on the mapper output records in the mapper task itself, so as to produce combined records. Now, one has to be careful while using combiner. So, we have used the combiner in case of the word count program, that is because so if we have, let us say, word W11, W11, then we can combine these to form W12 and give this to the output, give this to the reducer, which will again add. So, let us say reduce, this came from mapper 1, mapper 2 gave W1 3 and so on and so forth. So, the reducer can combine this to get an output W1 5. So, the count of the word W1 becomes 5. However, in certain mappers this may not be the case. So, for example, in certain reducers this may not be possible. So, for example, if your reducer is not commutative or associative, then this may not be possible. So, one needs to be careful while using the combiner. So, only if your reducer is commutative and associative can you use the combiner. So, an example of a reducer where you cannot use combiners is, for example, if your reducer is computing an average of the input numbers. So, as you can see, the average of averages is not the same as the average of the original list, okay. So, or the entire list of numbers. So, in that case the combiners will not work. Okay. And finally, as we have discussed that the bucketing in case of mappers is done by default using the hash of the mapper output key. However, you can use your custom partitioners which are very important sometimes if you want to take care of the skew in the key distribution. So, in that case, instead of using a simple hash partitioner, you can use something like a histogram partitioner, where basically the hashing function is used in a manner such that the approximate number of reducer input records for each part. So, the input is partitioned such that in addition to satisfying the fact that one key should go to one reducer, the number of records in going to each reducer is made roughly equal. And so with this, so in conclusion, we have seen some implementation details of MapReduce, specifically sort and shuffle, coordination between the map tasks, fault tolerance, pipelining and some refinements. So, this concludes our lecture on the Hadoop system, and these are the references for this lecture. Thank you.